On October 3, 2025, something strange happened in the Martian sky. Two spacecraft orbiting the red planet turned their cameras toward a visitor from beyond our solar system. The European Space Agency's ExoMars Trace Gas Orbiter and Mars Express captured images of an interstellar comet named 3I Atlas as it swept past Mars at a distance of about 30 million kilometers. These were among the closest pictures ever taken of an object that came from another star system, and what scientists saw in those images would spark heated debates that continue today. The comet appeared as a fuzzy white dot moving through a field of streaked stars, but it was what wasn't there that caught everyone's attention. Where scientists expected to see a long, bright tail streaming behind the comet, they found almost nothing. The tail was too dim to photograph properly, and that was just the beginning of the mysteries. Let's take a step back and talk about what makes this visitor so unusual. You see, for most of human history, we thought our solar system was pretty much alone in space. Sure, we knew there were other stars out there, billions and billions of them. But the space between those stars seemed empty, dark, and unreachable. Then, in 2017, astronomers discovered something that changed everything. They spotted an object tumbling through our solar system that didn't belong here. It wasn't orbiting the sun like a normal asteroid or comet. Instead, it was moving way too fast, following a path that meant it came from somewhere else, from the space between the stars. They named it Oumuamua, which means scout or messenger in Hawaiian, and it became the first confirmed interstellar object ever detected passing through our neighborhood. Oumuamua was weird, really weird. It looked like a long cigar or maybe a flat pancake spinning end over end as it zoomed away from the sun. It didn't have a tail like comets usually do, but it sped up slightly as if something was pushing it from behind. Scientists argued for years about what it could be. Was it a piece of a broken planet? A chunk of frozen hydrogen? Some researchers even wondered if it might be something built by an alien civilization, though most scientists thought that was extremely unlikely. Before anyone could get really good pictures or measurements, Oumuamua shot out of the solar system and disappeared into the darkness of space forever. 2 years later, in 2019, an amateur astronomer in Russia named Gennady Borisov discovered the second interstellar visitor. This one was different from Oumuamua. It looked like a regular comet, with a fuzzy cloud of gas and dust around its center and a tail pointing away from the sun. Scientists named it 2I Borisov, and they got much better observations because they spotted it while it was still approaching the sun, giving them months to study it. Borisov acted pretty much like comets that were born in our own solar system. It released water vapor and carbon monoxide as the sun heated it up. Its reddish color matched comets from our Oort cloud, the distant shell of icy objects that surrounds our solar system billions of kilometers from the sun. Then came 3I Atlas. On July 1st, 2025, a telescope in Chile called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, spotted something new in the sky. At first, nobody knew if it was a comet or an asteroid. It just looked like a faint dot moving against the background stars. But as more telescopes around the world swung around to look at it, astronomers started to realize they were seeing something special. The object was moving incredibly fast, about 250,000 kilometers per hour when it came closest to the sun. That's fast enough to travel from Earth to the moon in less than 2 hours. More importantly, it was moving so fast that the sun's gravity couldn't hold on to it. This thing was going to zip through our solar system and head back out into interstellar space, never to return. By early July, scientists confirmed that 3I Atlas showed cometary activity. There was a faint fuzzy cloud around its nucleus, what we call a coma, and possibly a small tail. The Minor Planet Center officially gave it the designation 3I, meaning it was the third interstellar object we had ever detected. Scientists everywhere got excited. Here was a chance to study another messenger from the stars, to learn about how other planetary systems form and what kinds of objects drift through the galaxy. NASA and other space agencies immediately started planning observations. The Hubble Space Telescope took pictures on July 21, 2025, when the comet was about 445 million kilometers from Earth. Those images showed a teardrop-shaped cocoon of dust streaming away from the icy nucleus. The James Webb Space Telescope, our most powerful space observatory, trained its instruments on 3I Atlas in early August. Webb's infrared sensors can detect heat and can peer through dust clouds that visible light cannot penetrate. What Webb found was surprising. The comet was wrapped in an unusually thick fog of carbon dioxide, much more than water vapour. Most comets in our solar system release mostly water when the sun heats them up, because they're made mostly of water ice. But 3I Atlas seemed to be made of something different. Here's where things start to get really interesting. Imagine you're a detective trying to figure out a mystery, and every new clue you find makes the case more puzzling instead of clearer. That's what happened with 3I Atlas. On August 6th, Webb observed the comet again and found not just carbon dioxide but also carbon monoxide, a gas called carbonyl sulfide, and small amounts of water ice and water vapour. The mix was unusual but not impossible for a comet. Some comets from the far reaches of our own solar system have similar compositions, but then scientists made another discovery that raised eyebrows. Using a big telescope in Hawaii called the Keck Observatory, astronomers observed 3I Atlas on August 24th and detected something strange in the gases around the comet. They found lots of nickel vapour but very little iron. Now that might not sound weird until you realise that in nature, nickel and iron almost always go together. When stars explode or when rocky planets form, these two metals stick together like best friends. Finding nickel without iron is like finding peanut butter sandwiches without any bread anywhere nearby. It just doesn't happen naturally. The only place scientists know where you get lots of nickel without iron is in certain industrial metal alloys that humans make in factories. Of course, nobody is saying aliens built 3I Atlas in some cosmic factory. But it's definitely strange, and scientists don't have a good natural explanation yet. Let's think about the journey this object has taken to reach us. When 3I Atlas was first spotted in July, scientists calculated that it was travelling at about 58 km per second relative to the Sun. That's much faster than the two previous interstellar visitors. Oumuamua travelled at 26 km per second and Borisov at 32 km per second. The high speed of 3I Atlas tells us something important. It suggests this object might be incredibly old, possibly one of the oldest comets ever observed. Picture this. About 11 billion years ago, when the universe was less than a quarter of its current age, a young star system was forming somewhere in our galaxy. Clouds of gas and dust swirled around a newborn star, gradually clumping together to form planets and moons and comets. But not all the material stayed in that system. Maybe a giant planet like Jupiter flung some icy chunks away with its powerful gravity, or maybe two planets crashed into each other and sent debris flying in all directions. However it happened, a chunk of ice and rock escaped that star system and began drifting through interstellar space. For billions of years, this object travelled alone through the darkness between the stars. It moved through clouds of dust and gas, through regions where new stars were being born, through the spiral arms of the Milky Way galaxy. Cosmic rays, which are super high energy particles that zoom through space at nearly the speed of light, constantly bombarded its surface. These cosmic rays can actually change the chemistry of ice, breaking apart water molecules and creating new substances. Some scientists think this is why 3I Atlas has such unusual chemistry. After an unimaginably long journey, this ancient wanderer finally entered our solar system in 2025. By cosmic coincidence, we happen to have the technology to detect it and the spacecraft positioned to study it up close. As 3I Atlas approached the inner solar system in the summer of 2025, it got closer and closer to the Sun. The Sun's heat started to warm the comet's surface, causing ices to turn directly into gas without becoming liquid first, a process called sublimation. Think about dry ice, which is frozen carbon dioxide. If you leave dry ice out on a table, it doesn't melt into a puddle. Instead, it turns straight into carbon dioxide gas and disappears into the air, creating that cool, misty effect. The same thing happens to comets as they approach the Sun. The ices on and below their surfaces sublimate, releasing gas that carries dust particles with it. This creates the coma, the fuzzy cloud around the nucleus, and the tail that streams away from the Sun, pushed by sunlight and the solar wind. But 3I Atlas wasn't behaving quite like scientists expected. In late May and early June, before it was discovered, NASA's TESS satellite had actually photographed the comet without realizing it. Later, when scientists went back and looked at those old images, they stacked thousands of frames together to create a very deep picture. What they found was puzzling. The comet looked just like a dot similar to nearby asteroids. There was no extended coma, no fuzzy halo of gas and dust. This meant that in late May, 3I Atlas was either completely inactive or it was only releasing a tiny amount of gas and dust that couldn't be detected. Then, just a few weeks later in early July when other telescopes spotted it, there was suddenly a coma. The comet had turned on. Scientists wondered why. What changed between late May and early July? As July turned to August and then September, 3I Atlas continued its approach toward the Sun. On September 7th, astronomers used a special telescope in Hawaii called the James Clerk Maxwell Telescope to observe the comet. This telescope detects radio waves instead of visible light. What it found was even more mysterious. The comet was releasing enormous amounts of hydrogen cyanide, a poisonous gas that's also found in many comets from our solar system. On September 7th, 3I Atlas was pumping out about 1.5 followed by 25 zeros molecules of hydrogen cyanide every second. That's an incomprehensibly huge number. By September 14th, just 1 week later, the production rate had tripled. The coma of cyanide gas had grown to about 180,000 kilometers across, which is about 14 times the width of Earth. An odd detail caught scientists' attention, though. The cyanide cloud wasn't symmetric. It was stretched out in the direction away from the Sun, as if the comet was leaving a trail behind it as it moved. Around this same time, another strange feature appeared. Some observations showed what looked like a second tail pointing in an unusual direction. Most comet tails point away from the Sun because they're pushed by sunlight and the stream of particles constantly flowing, out from the Sun called the solar wind. But this second tail seemed to point partly toward the Sun, which doesn't make normal sense. Now, to be fair, sometimes comets can appear to have what's called an antitail, but that's usually just an optical illusion caused by our viewing angle from Earth. When a comet passes between Earth and the Sun, we might see dust that was left behind earlier in its orbit, creating the illusion of a tail pointing the wrong way. But some scientists studying 3I Atlas wondered if this was something different, something that hadn't been seen in regular comets before. Then came the big event. Remember how I mentioned at the beginning that 3I Atlas passed close to Mars on October 3rd? That was a huge opportunity. Earth was on the opposite side of the Sun at that time, so telescopes on Earth couldn't get a good view. The comet was basically hiding behind the Sun from our perspective. But Mars, along with all the spacecraft orbiting Mars, had a front row seat. Multiple Mars orbiters prepared to observe this historic event. NASA's Mars Reconnaissance Orbiter, which carries a super powerful camera called HiRISE that can see details as small as a desk from orbit, pointed toward the comet. ESA's two Mars orbiters, ExoMars Trace Gas Orbiter and Mars Express, also aimed their instruments at 3I Atlas. The United Arab Emirates Hope Orbiter and China's Tianwen-1 mission were also positioned to potentially catch a glimpse. The observations were challenging. These cameras and instruments were designed to photograph the bright surface of Mars from just a few hundred or few thousand kilometers away. Now they had to look at a dim object millions of kilometers away, an object that was 10,000 to 100,000 times fainter than Mars itself. It's like trying to photograph a single candle from 100 kilometers away while standing next to a searchlight. The teams had to carefully plan the exposures, the length of time the camera shutter stays open. Too short and they wouldn't collect enough light to see anything. Too long, and the background stars would create streaks across the image, making it harder to spot the comet. ExoMars Trace Gas Orbiter succeeded in capturing images using 5-second exposures with its camera called CASSes. The resulting images, which the European Space Agency released to the public, showed a slightly fuzzy white dot moving downward through the frame against a background of streaked stars. That fuzzy dot was 3I Atlas, 30 million kilometers away from the spacecraft. The fuzzy appearance came from the coma, the cloud of gas and dust surrounding the nucleus. Scientists could see that the comet was active, releasing material into space. But what they couldn't see was just as important as what they could see. They couldn't photograph the nucleus itself because it was too small, estimated to be only about 1 kilometer across at most, and they couldn't capture a clear image of the tail. The ESA scientists said the tail was much dimmer than the coma, too faint for the camera to detect at that distance. Now here's where things get controversial. When those Mars images hit the internet, people started seeing things. One set of images from NASA's Perseverance rover on Mars taken on October 4th showed what appeared to be a long, bright, cylindrical object streaking through the Martian sky. Social media exploded with speculation. Some people wondered if this was proof that 3I Atlas wasn't a natural comet at all. Was it some kind of spacecraft? An alien probe? The images certainly looked strange, showing an elongated bright streak rather than a fuzzy ball. But there's a much simpler explanation that most scientists accept. The rover's camera wasn't designed to photograph fast-moving objects in the sky. When you take a picture of something that's moving, and your camera is set to snap multiple quick pictures in a row, then combine those pictures into one image, the moving object creates a long streak. It's the same effect you see in long exposure photographs of car headlights at night, where a moving car appears as a long line of light rather than a car shape. Most experts believe that's exactly what happened here. The cameras captured the motion of the object, probably even the Martian moon Phobos rather than the comet, and created an artifact that looked unusual but wasn't showing the actual shape of anything. Even with that explanation, a Harvard astronomer named Avi Loeb has been raising questions that make other scientists uncomfortable. Loeb is well known in the astronomy community for being open to unconventional ideas, including the possibility that some interstellar objects might not be natural. He's pointed out several things about 3I Atlas that he finds suspicious. Let's walk through his main points, even though most other scientists disagree with his conclusions. First, he notes that 3I Atlas has a very unusual trajectory. Its path through space lies within just 5 degrees of the ecliptic plane, which is the flat disk where all the planets orbit the Sun. Loeb calculated that there's only a 0.2% chance of this happening randomly. Most objects from interstellar space would approach from random directions since space has no up or down and no preferred plane. The fact that 3I Atlas came in nearly along the same plane as the planets strikes him as odd. Second, the timing of its arrival seemed remarkably convenient, Loeb argues. The comet's path took it past Mars in early October, then past Venus in early November, and it will pass relatively close to Jupiter in March 2026. Mars, Venus, and Jupiter are all worlds that scientists find interesting in the search for life beyond Earth. Mars once had liquid water on its surface, and might still have life underground. Venus, despite being brutally hot, has clouds where some scientists think microbial. Life could potentially exist, and Jupiter's moon Europa almost certainly has a vast ocean beneath its icy crust. Loeb calculated the odds of an interstellar object randomly passing near all 3 of these worlds and came up with a number around 0.005%. To him, that seems like too much of a coincidence. Third, Loeb points to the unusual size estimate. Based on various measurements, 3I Atlas appears to have a nucleus diameter possibly larger than 5 kilometers. That would make it much, much bigger than the previous 2 interstellar visitors, perhaps 1,000 to 1,000,000 times more massive. If it's that big, why did it take so long to spot? And how does something that large get ejected from a planetary system and sent drifting through interstellar space? Smaller objects are easier to fling away, but big objects need tremendous energy to escape a star's gravity. Fourth, there's the strange forward jet that Hubble spotted. When Hubble photographed 3I Atlas on July 21st, it showed a plume of scattered sunlight pointing toward the Sun, not away from it. This jet was about 10 times longer than it was wide. While jets aren't unusual in comets, they typically point in various directions based on where active vents are located on the rotating nucleus. A strong jet pointing directly toward the Sun seemed odd to some observers, though others thought it could be explained by the comet's rotation and the location of active spots on its surface. Fifth, we come back to that nickel without iron detection. Loeb emphasized that this chemical signature is only known to exist in certain industrial alloys that humans make artificially through a process called the carbonyl pathway. In space, nickel and iron form together in exploding stars and remain together when planets and asteroids form. Seeing one without the other is genuinely puzzling. Sixth, there's the trajectory alignment with something called the WOW signal. Back in August 1977, a radio telescope in Ohio detected a powerful narrowband radio signal from space that lasted 72 seconds. The signal was so surprising that an astronomer wrote WOW on the printout, and it's been called the WOW signal ever since. No one ever figured out what caused it, though most scientists think it was probably some kind of unusual natural phenomenon rather than an alien transmission. Loeb noticed that if you trace 3I Atlas's trajectory backward through space, its arrival direction aligns within about 9 degrees of where the WOW signal came from, though that region of sky was observed 50 years ago and stars have moved since then. Loeb calculates that there's about a 0.6% chance of this alignment happening by coincidence. 7th, Loeb noted unusual observations of what looked like 3I Atlas growing brighter in an unexpected way. As the comet approached its closest point to the Sun on October 30th, some observations showed it becoming distinctly bluer in colour rather than redder. Dust typically makes scattered sunlight look more reddish, like how sunsets look red because sunlight scatters through the atmosphere. Also, the surface of a comet should be much colder than the Sun's surface, which should make it look redder, not bluer. Loeb wondered if the blue colour might suggest some kind of power source hotter than the Sun's surface, though other scientists suggested more mundane explanations like the particular gases being released or measurement uncertainties. 8th, there's what some have called the anomalous anti-tail, that second tail pointing in an unusual direction that I mentioned earlier. And 9th, there's simply the cumulative effect of all these oddities happening in one object. Now, before we get too caught up in the mystery, let's be very clear about something. The vast majority of scientists who study comets think 3I Atlas is exactly what it appears to be, a natural comet from another star system. Tom Statler, NASA's lead scientist for solar system small bodies, told reporters that while 3I Atlas does have several interesting properties, it behaves like a comet, and the evidence is overwhelmingly pointing to this object being a natural body. The unusual features can be explained without invoking anything extraordinary. The carbon dioxide-rich composition might simply tell us that the comet formed in the outer regions of its home star system, far from the star where carbon dioxide ice is more stable than water ice. The nickel without iron detection might be a measurement issue or might reveal something about how certain types of cosmic dust behaves that we simply don't understand yet. The large size estimate might be wrong because measuring the size of something so small and distant is incredibly difficult. The trajectory alignment with the ecliptic plane might just be chance, or it might tell us something about the average motion of stars in our region of the galaxy. And the other oddities might simply reflect the fact that we've only studied 3 interstellar objects ever, so we don't really know what's normal and what's unusual yet. Think about it this way. If you only ever met 3 people from a foreign country, and those 3 people all looked and acted somewhat differently from each other, could you confidently say what people from that country are typically like? Of course not. You'd need to meet hundreds or thousands of people to understand the normal range of variation. It's the same with interstellar objects. We've seen 3 of them. That's not enough to know what's typical and what's weird. Maybe all interstellar comets are rich in carbon dioxide. Maybe nickel-rich dust is common in certain types of star systems. Maybe we're just seeing natural variation, and our human brains are trying to find patterns where none exist. But here's the beautiful thing about science. We don't have to just sit around, arguing. We can collect more data. ESA's Jupiter mission called JUICE, which stands for Jupiter Icy Moons Explorer, attempted to observe 3I Atlas in November 2025. JUICE is currently travelling through space on its way to Jupiter, where it will study the giant planet's icy moons Europa, Ganymede, and Callisto. When it pointed its instruments at 3I Atlas in November, the comet was just past its closest approach to the Sun and should have been at peak activity, releasing the maximum amount of gas and dust. JUICE's cameras and spectrometers might reveal more details about the comet's composition and behaviour. The data from JUICE won't arrive until February 2026 because the spacecraft is currently using its main antenna as a heat shield while it's close to the Sun, so it can only send data very slowly using a smaller antenna. Meanwhile, scientists are still analysing all the data from the Mars observations in October. They're looking at spectroscopic data, which breaks down light into its component colours to reveal what chemicals are present. Different molecules absorb and emit light at specific wavelengths, creating what's almost like a fingerprint that identifies what substances are there. By studying the spectrum of light from 3I Atlas's coma, scientists can figure out what gases it's releasing. They're also studying the images from multiple angles and times to understand how the comet's activity changes as it rotates, and as it gets closer to or farther from the Sun. 3I Atlas reached its closest point to the Sun, called perihelion, on October 30th, 2025, passing about 203 million kilometers from the Sun. That's between the orbits of Earth and Mars. At that point, the comet was receiving maximum sunlight and should have been most active. After perihelion, it started moving away from the Sun, heading out of the inner solar system. On November 3rd, it passed about 97 million kilometers from Venus. On December 19th, It will pass about 269 million kilometers from Earth. That's still pretty far away, nearly twice the distance from Earth to the Sun, so unfortunately we won't get spectacular views from Earth. Then, in March 2026, it will pass about 54 million kilometers from Jupiter. Some scientists hope that NASA's Juno spacecraft, which is currently orbiting Jupiter, might be able to observe 3I Atlas during that encounter. After the Jupiter flyby, 3I Atlas will continue accelerating as it climbs away from the Sun, gradually heading back toward interstellar space. Eventually, probably sometime in the late 2020s or early 2030s, it will cross the boundary of the solar system and return to the darkness between the stars. It will never come back. This is our only chance to study it. In a few decades or centuries, 3I Atlas will have travelled so far that even our most powerful telescopes won't be able to detect it anymore. It will become invisible, just another grain of ice and rock drifting through the vast emptiness, carrying with it whatever secrets it hasn't revealed to us. Let's zoom out for a moment and think about the bigger picture. Why should we care about these interstellar visitors? What's so important about studying chunks of ice from other star systems? Well, these objects are like messages in bottles, except instead of bottles floating across the ocean, they're pieces of other worlds floating across the galaxy. Every star system forms differently. The distances between planets, the types of gases available, the amount of heavy elements like carbon and oxygen, the presence or absence of giant planets like Jupiter, all of these factors influence what kinds of comets and asteroids form. By studying interstellar objects, we're essentially sampling the building blocks from other planetary systems. We can compare them to objects from our own solar system and start to understand whether our Sun's family of worlds is typical or unusual. These visitors also remind us of a humbling truth about our place in the cosmos. We tend to think of the solar system as our neighbourhood, a place that's separate from the rest of the galaxy. But the galaxy doesn't work that way. The space between stars isn't empty. It's filled with wandering objects, rouge planets that were kicked out of their star systems, icy comets drifting for billions of years, pieces of shattered worlds, and clouds of gas and dust. Our solar system is constantly sailing through this material as the Sun orbits around the centre of the Milky Way galaxy. Some of that interstellar material even makes it all the way to Earth. Scientists have found tiny grains of dust in Antarctic ice and in meteorites that formed around other stars billions of years ago. We're constantly being sprinkled with stardust from across the galaxy, most of it too small to notice. Oumuamua, Borisov, and now 3I Atlas are just the larger pieces that we happen to spot. Scientists estimate that there's probably at least one interstellar object inside Earth's orbit at any given time, and maybe 10,000 throughout the whole solar system. We just don't see most of them because they're too small and too dark. But that's about to change. In early 2025, a new observatory called the Vera Rubin Observatory began operations in Chile. This facility has an enormous camera that can photograph the entire southern sky every few nights, automatically searching for anything that moves or changes. Scientists predict that the Rubin Observatory will detect between 1 and 3 interstellar objects, like 3I Atlas every year, and possibly many more that show clear cometary features. In a few years, instead of having studied 3 interstellar visitors, we might have data on dozens or hundreds. That flood of new discoveries will transform our understanding. We'll be able to start answering questions like, what's the typical composition of interstellar comets? Do most of them contain more water or more carbon dioxide? How big are they usually? Where do they come from? Right now, we're basically guessing based on 3 examples. Soon, we'll have real statistics. We'll also learn more about how common planetary systems are in our galaxy and how they typically evolve. When gas giant planets form and migrate, they fling smaller objects into interstellar space. By studying the population of interstellar visitors, we can estimate how often this happens and how many exoplanets might exist. There's also a practical reason to care about these objects. Although 3I Atlas and the other interstellar visitors we've seen pose no threat to Earth, someday we might spot one that's on a collision course with our planet. It's incredibly unlikely, but not impossible. If that happened, we'd need to understand what these objects are made of and how they behave in order to deflect them or destroy them before impact. Studying peaceful visitors like 3I Atlas helps us prepare for that possibility, even though we hope it never happens. Let's talk about what happens next in the story of 3I Atlas. Right now, In mid-November 2025, the comet is moving away from the Sun and slowly fading as it cools down. The sunlight is weaker out here, so less ice is sublimating, and the coma and tail are shrinking. Astronomers on Earth who have access to large professional telescopes can still track it, but it's getting harder to see. By early 2026, it will be so faint that only the biggest telescopes with the most sensitive cameras will be able to photograph it. But scientists will keep watching for as long as possible. Every additional observation helps refine our understanding of its orbit, its size, its composition, and its behavior. Teams around the world are writing research papers about 3I Atlas, analyzing data and testing hypotheses. Some are building computer models to simulate how an object with 3I Atlas's properties might have formed and evolved. Others are comparing its chemical composition to meteorites and comets from our solar system to look for similarities and differences. Still others are trying to figure out where in the galaxy it might have come from. When you trace its trajectory backward through space, accounting for the motion of stars and the complex gravitational dance of the Milky Way, you can sometimes narrow down a region where the object might have originated. Scientists have done this for the previous interstellar visitors with mixed results. For 2I Borisov, researchers identified several candidate home stars, though they couldn't be certain. For 3I Atlas, similar work is ongoing. One thing that makes this detective work difficult is that 3I Atlas has been travelling for such a long time. If it really is billions of years old as its high speed suggests, then the stars in our galaxy have moved substantially since it was ejected from its home system. Imagine trying to figure out where a ship came from when the ship has been sailing for 10,000 years and all the ports have moved to different locations. That's essentially what astronomers are attempting. Despite the challenges, there's hope that eventually, with enough data from the Rubin Observatory and other sky surveys, we might identify the general region of the galaxy where 3I Atlas was born. Now, I want to address the elephant in the room. Could 3I Atlas be anything other than a natural comet? Is there any serious possibility that it's a probe or spacecraft from an alien civilization? Most scientists say no for several good reasons. First, nothing about its behavior requires an artificial explanation. Everything we've observed can be explained, even if some of the explanations are uncertain, by natural processes. Second, if you were an advanced civilization capable of sending something across interstellar space, why would you make it look like a comet? You'd probably want your probe to be protected from impacts with dust grains, which means you'd encase it in something solid, not in sublimating ice that boils away as you approach stars. You'd also probably want to slow down and enter orbit around interesting planets to study them, not zip through the solar system at 250,000 kilometers per hour and leave forever. Third, we need to be careful about assuming that unusual means artificial. Humans have a tendency to see patterns and intelligence in random events, a psychological quirk called pareidolia. It's why we see faces in clouds and animals in rock formations. When we encounter something we don't immediately understand, our brains sometimes jump to the most exciting explanation, rather than the most likely one. In science, we have a principle called Occam's razor, which says that when you have multiple explanations for something, the simplest one that requires the fewest assumptions is usually correct. The simplest explanation for 3I Atlas is that it's a natural comet with some unusual but not impossible properties. The more complex explanation that it's an artificial object requires us to assume that aliens exist, that they have technology far beyond ours, that they sent something to our solar system, that they designed it to look exactly like a comet, and that they timed its arrival for reasons we can't fathom. That's a lot of assumptions. None of this means we should ignore the strange features of 3I Atlas or stop asking questions. Science advances by investigating anomalies and puzzles. Sometimes those investigations lead to boring answers, and sometimes they revolutionize our understanding of the universe. The key is to remain curious but skeptical, open-minded but not gullible. We should follow the evidence wherever it leads, but we should also demand good evidence before accepting extraordinary claims. As the astronomer Carl Sagan famously said, extraordinary claims require extraordinary evidence. Right now, the evidence suggests 3I Atlas is a natural object, but scientists will keep studying it to be sure. Let's imagine what we might learn if we could visit 3I Atlas up close. Suppose we had sent a spacecraft to intercept it. What would we see? Well, the nucleus, the solid core of the comet, is probably shaped like a lumpy potato, as most comets are. It might be anywhere from a few hundred meters to a few kilometers across, depending on which size estimate is correct. Its surface would be dark, darker than asphalt, because cosmic rays and ultraviolet light have altered the ice and created a crust of complex organic compounds called tholins. These tholins are the same materials that give many outer solar system objects their reddish or brownish colours. If our imaginary spacecraft could land on the surface, we'd find a landscape unlike anything on Earth. The gravity would be incredibly weak, so weak that you could jump several kilometres into space if you weren't careful. The surface would be covered in a layer of dust and pebbles, possibly with patches of ice showing through in places. Here and there, we might see active vents or cracks where gas is escaping from below, carrying fine dust with it. These jets might glow faintly in sunlight as the escaping gas scatters light. The sky would be black even during the day, just like on our moon, because there's no atmosphere to scatter light. The sun would look smaller than it does from Earth because we're farther away, but it would still be bright enough to light up the comet's surface. If we could analyse samples of the ice and rock, we'd learn exactly what this comet is made of. We'd be able to measure the ratios of different types of atoms, called isotopes, which serve as fingerprints for where and when something formed. We could look for complex organic molecules, the carbon-based compounds that are the building blocks of life. Finding such molecules wouldn't mean we'd found life, because these compounds form naturally in space, but it would tell us about the chemistry of the planetary system where 3I Atlas was born. We might even find tiny grains of pre-solar dust, material that existed before the sun formed, providing a direct sample of the interstellar medium from billions of years ago. Of course, we didn't send a spacecraft to 3I Atlas. We couldn't. The object was discovered in July 2025, and it passed through the inner solar system just a few months later. Building and launching a spacecraft takes years of planning and billions of dollars. By the time we even confirmed what 3I Atlas was, it was already too late to catch it. This is one of the biggest frustrations in studying interstellar objects. They arrive without warning and leave, quickly, giving us only a brief window to observe them. That's why scientists are so eager to detect these visitors earlier, while they're still far from the sun and we have more time to plan observations or even missions. There's actually a proposal called the Bridge Program that aims to develop a rapid response spacecraft that could be launched quickly to intercept interstellar objects. The idea is to have a probe ready to go, sitting in storage, waiting for the next Oumuamua or Borisov or 3I Atlas. When astronomers detect a new interstellar visitor, the spacecraft could be launched within weeks or months and use a fast trajectory to catch up with the object before it leaves the solar system. Such a mission would be challenging and expensive, but it might be the only way to get close-up data on these rare messengers from other star systems. So far, the Bridge program hasn't received full funding, but interest is growing, especially after the discoveries of the past few years. Meanwhile, scientists are working on improving our ability to detect interstellar objects sooner. The challenge is that these objects are small and dark and moving fast. Most telescopes are designed to look at stars or galaxies that stay in one place, or to track asteroids and comets that orbit the sun predictably. Interstellar objects don't follow the rules. They come from random directions and move much faster than solar system objects. To spot them early, we need telescopes that can scan huge areas of sky repeatedly, looking for anything that moves in an unusual way. The Vera Rubin Observatory I mentioned earlier is perfect for this job. Its giant camera can photograph an area of sky about 40 times the size of the full moon in a single image, and it can repeat the entire sky every few nights. Powerful computers compare each new image to previous ones, automatically flagging anything that has moved or changed. When the Rubin Observatory is running at full capacity, it might detect an interstellar object while it's still beyond Jupiter's orbit, giving us months or even years of warning instead of just weeks. That would be a game changer. With months of warning, scientists could coordinate observations across dozens of telescopes worldwide. They could schedule time on space telescopes like Hubble and James Webb. They might even be able to redirect a spacecraft already in space to fly past the interstellar visitor. NASA has several missions in the outer solar system, like New Horizons, which flew past Pluto and is now heading into the Kuiper Belt. If an interstellar object happened to pass near one of these spacecraft, mission controllers could potentially alter the spacecraft's trajectory slightly to get a closer look. It would take incredible luck for such an encounter to happen, but with more detections, luck becomes more likely. Let's take a moment to recap what we know for sure about 3I Atlas, stripping away the speculation and controversy. We know. It's an object from outside our solar system, confirmed by its trajectory and speed. We know it's releasing gas and dust like a comet, creating a visible coma and at least one tail. We know its composition is unusual, rich in carbon dioxide and carbon monoxide, with less water than typical solar system comets. We know it has a reddish colour consistent with many comets and asteroids we've seen before. We know it passed close to Mars in October and close to Venus in November, and it will pass relatively close to Jupiter in March 2026. We know its nucleus is probably quite small, maybe 1 to 5 kilometres across, though the exact size remains uncertain, and we know it will leave the solar system forever within the next few years, returning to interstellar space from which it came. What we don't know is just as important. We don't know exactly where 3I Atlas came from, which star system ejected it billions of years ago. We don't know why its chemical composition is so different from the previous 2 interstellar visitors. We don't know why it seems to have activated suddenly in early July rather than gradually as it approached the Sun. We don't know for certain how big it really is. We don't fully understand the nickel-rich, iron-poor vapour that was detected. We don't know if the unusual features that caught Avilobe's attention are genuinely mysterious, or if they're just artifacts of limited observations and our own lack of experience with interstellar objects. And we certainly don't know if there's anything unnatural about it, though most scientists strongly doubt that possibility. The honest truth is that 3I Atlas remains an active area of research. Scientists are still analysing data, writing papers, debating interpretations, and planning future observations. The story isn't over yet. New results will continue to emerge throughout 2026 and beyond. Some of those results might resolve the current mysteries, explaining away the oddities with natural processes we already understand. Other results might deepen the mystery, revealing features that are even harder to explain. That's the beautiful thing about science. It's a process of discovery that never really ends. Every answer leads to new questions, and every mystery solved reveals new puzzles to explore. Now, before we move on to talk about related objects in the space community, let me leave you with a thought about what 3I Atlas represents. This small chunk of ice and rock has travelled farther and longer than anything humans have ever made. Our most distant spacecraft, Voyager 1, has been travelling for almost 50 years and has covered about 24 billion kilometres. That sounds like a lot, and it is by human standards. But 3I Atlas has travelled for billions of years, covering distances so vast that light itself would take thousands or millions of years to travel the same path. This object is older than our Sun, older than Earth, possibly older than many of the stars you see in the night sky. It has witnessed the birth and death of stars. It has drifted through nebulae where new solar systems are forming. It has survived impacts with interstellar dust and bombardment by cosmic rays. And now, for just a brief moment in its incomprehensibly long journey, it has passed through our little corner of the galaxy, giving us a glimpse of the cosmos beyond our solar system. Whether 3I Atlas is a completely normal comet with a few unusual but explainable features, or whether it represents something we don't yet understand about how comets form and behave, one thing is certain. It has reminded us that we are not alone in the galaxy, not in the sense of finding alien civilizations, but in the sense that we're connected to the rest of the universe in ways we're only beginning to understand. The material that makes up our bodies, the atoms in every cell, were cooked inside stars that exploded before the Sun was born. Some of those atoms might have drifted through space as interstellar dust before being incorporated into the cloud that formed our solar system. In a very real way, we are made of the same stuff that 3I Atlas is made of, stardust that has been cycling through the galaxy for billions of years. 3I Atlas is a reminder of that connection, a piece of someone else's solar system visiting ours, a cosmic pen pal from across the galaxy. Before 3I Atlas and before 2I Borisov, there was Oumuamua, the object that changed everything. On October 19, 2017, a telescope in Hawaii called Pan-STARRS, which stands for Panoramic Survey Telescope and Rapid Response System, detected a faint point of light moving rapidly across the sky. At first, astronomers thought it was just another asteroid or maybe a comet from the outer reaches of our solar system. They gave it a temporary designation and prepared to track it for a few nights to figure out its orbit. But when they calculated the orbit, something shocking became clear. This object wasn't orbiting the Sun at all. It was moving far too fast, travelling at about 87,000 kilometers per hour relative to the Sun. More importantly, its trajectory was hyperbolic, a type of path that means the object came from somewhere else and will never return. Scientists quickly realized they were witnessing something that had never been observed before in human history, an object from interstellar space passing through our solar system. The discovery sent waves of excitement through the astronomy community. Within days, telescopes all over the world swung around to observe this mysterious visitor. They needed to collect as much data as possible, because Oumuamua, as it would soon be named, was already leaving. It had passed closest to the Sun back in September, before anyone knew it existed, and by the time of discovery it was already racing outward, heading back toward interstellar space. The name, Oumuamua, comes from Hawaiian and means scout or messenger, or more poetically a messenger from afar arriving first. It was a perfect name for humanity's first confirmed interstellar visitor. Hawaiian astronomers suggested the name because the Discovery Telescope was located in Hawaii, and the Hawaiian language has a rich tradition of names connected to voyaging and exploration. The name was officially adopted, and Oumuamua became a household word, at least among people who follow space news. As observations poured in during late October and November 2017, Oumuamua revealed itself to be deeply strange. First, its shape appeared to be highly elongated, nothing like the roughly spherical or potato-shaped asteroids we're used to seeing. Based on how its brightness changed as it tumbled through space, astronomers calculated that Oumuamua was at least 5 to 10 times longer than it was wide. Some estimates suggested it might be shaped like a cigar or a cucumber, perhaps 400 meters long but only 40 meters wide. Other researchers thought it might be shaped more like a pancake or a disc, flat and round but very thin. Either way, it was unlike any asteroid or comet anyone had seen before. Objects in our solar system just don't naturally form those extreme shapes, at least not commonly. Second, Oumuamua was tumbling chaotically through space, rotating around multiple axes at once. Imagine throwing a football while also spinning it sideways. That's roughly what Oumuamua was doing. This tumbling made it difficult to study because its brightness kept changing as different parts of its surface faced toward or away from telescopes on Earth. Every few hours, the amount of light reflecting off Oumuamua would change by a factor of 10, suggesting a very elongated shape presenting different cross-sections as it spun. Third, and perhaps most puzzling, Oumuamua didn't look like a comet. When comets approach the Sun, the heat causes ices on their surface to sublimate, creating a fuzzy coma of gas and dust and usually a long tail. Astronomers looked carefully for any signs of cometary activity around Oumuamua and found nothing. There was no coma, no tail, no evidence of gas or dust escaping. It looked like a bare rock tumbling through space. This suggested Oumuamua might be more like an asteroid, a chunk of solid rock and metal rather than ice. But that created its own mysteries because asteroids from other star systems were expected to look and behave differently from comets. Then, in June 2018, 7 months after the discovery, researchers published a finding that reignited all the debates about Oumuamua's nature. They had carefully analysed its trajectory, using all the available observations, and discovered something unexpected. Oumuamua was accelerating. Not much, just a tiny bit, but definitely speeding up as it moved away from the Sun. This acceleration couldn't be explained by gravity alone. Something was pushing Oumuamua, giving it a little extra speed. The most obvious explanation was that Oumuamua was actually a comet after all, and that escaping gas was creating a small rocket effect, pushing the object forward. This is called outgassing, or non-gravitational acceleration, and it's completely normal for comets. The problem was that telescopes hadn't detected any gas or dust around Oumuamua. If it was outgassing enough to cause the observed acceleration, there should have been visible evidence. This is where things got controversial. Some scientists proposed that Oumuamua might be made of unusual materials that outgas in ways we don't normally see. For example, if it was made largely of nitrogen ice, like the surface of Pluto, it might sublimate without creating a visible coma. Or if it was made of hydrogen ice, the escaping gas would be invisible to most telescopes. Others suggested that Oumuamua might not be outgassing at all. Maybe the acceleration came from sunlight pressure. Light from the Sun actually pushes on objects, though the force is usually too weak to matter for anything except very lightweight things like solar sails. If Oumuamua was extremely thin, like a sheet of paper or a giant snowflake, then sunlight pressure might explain the acceleration. This pancake shape theory became popular for a while, though it raised new questions about how such an object could form naturally. Then came the really wild ideas. Avi Loeb, the same Harvard astronomer who has raised questions about 3I Atlas, co-authored a paper suggesting that Oumuamua might be an artificial object, perhaps a light sail built by an alien civilization. A light sail is a spacecraft that uses enormous ultra-thin mirrors to catch sunlight and sail through space without needing rockets or fuel. Loeb argued that an artificial light sail would explain Oumuamua's strange shape, its unusual acceleration, and its lack of visible outgassing. He was careful to say this was just one possibility among many, and that more data was needed. But the media jumped on the idea, and headlines around the world proclaimed that Oumuamua might be an alien spacecraft. Most astronomers strongly disagreed with this interpretation, arguing that natural explanations were far more likely and that invoking aliens was unnecessary and premature. The controversy highlighted a tension in science between being open to unconventional ideas and being appropriately skeptical of extraordinary claims. As months turned into years, and Oumuamua receded into the distance, becoming too faint for even the most powerful telescopes to detect, the debates continued. Researchers published dozens of papers proposing different explanations for its properties. Some suggested it was a fragment of a planet that had been destroyed, perhaps when a giant impact shattered a Pluto-like world in another star system. Others proposed it was a piece of molecular hydrogen ice, held together by weak chemical bonds. Still others thought it might be a fractal dust aggregate, a fluffy collection of microscopic dust grains bound by static electricity. Each theory had its strengths and weaknesses, but without more data it was impossible to be sure. One team of scientists tried to trace Oumuamua's trajectory backward through the galaxy to figure out where it came from. They accounted for the motion of stars and the gravitational influences of the Milky Way, and eventually narrowed down a few candidate home systems. None of the candidates were definitive, though. Space is big, and stars have moved a lot since Oumuamua began its journey millions or billions of years ago. The best the researchers could say was that Oumuamua probably came from the general direction of the constellation Lyra, where the bright star Vega shines, but even that wasn't certain. What we know for absolute certain about Oumuamua is actually quite limited. We know it came from interstellar space. We know it passed through the inner solar system in mid-2017. We know it had an unusual reddish colour, similar to objects in the outer parts of our own solar system that have been exposed to cosmic radiation for billions of years. We know it was small, somewhere between 100 and 400 meters long, depending on its exact shape and composition. We know it experienced a small non-gravitational acceleration that hasn't been definitively explained. And we know it's gone now, invisible to our telescopes, carrying its secrets back into the darkness between the stars. The legacy of Oumuamua is profound. It proved that interstellar objects do pass through our solar system, turning a theoretical possibility into observed reality. It showed us that these visitors can have properties very different from anything in our own solar system, expanding our understanding of what's possible. It inspired new research programs and telescope surveys designed to find more interstellar visitors, and it sparked public imagination in a way that few astronomical discoveries do, reminding millions of people that we live in a dynamic galaxy where the space between stars is far from empty. Every child who learned about Oumuamua in school, every adult who read news articles about it, came away with a slightly different understanding of the universe, one where our solar system is not isolated but constantly interacting with the broader galaxy. Looking back now in late 2025, Oumuamua seems like the beginning of a new era in astronomy. Before 2017, interstellar objects were a purely theoretical concept. Now, they're an active field of research with observational data, ongoing surveys, and even mission proposals. Oumuamua was the scout, the first messenger, and it delivered its message clearly. The galaxy is full of wanderers, and if we watch carefully, we'll see them passing by. On August 30th, 2019, an amateur astronomer named Gennady Borisov was doing what he loved, scanning the night sky with a telescope he had built himself. Borisov lives in Crimea and works at the Margot Observatory, but his Discovery telescope was his own creation, a 65-centimetre reflector that he designed and assembled in his spare time. On that particular night, he was photographing a region of sky in the constellation Cancer when he noticed something unusual, a faint fuzzy object that hadn't been there in previous images. He reported the discovery, and professional astronomers quickly followed up with their own observations. Within a few days, it became clear that Borisov had found something remarkable, the second known interstellar object passing through our solar system. The object was officially designated 2I/Borisov, with the 2I indicating it was the second interstellar visitor ever detected. Unlike Oumuamua, which had been discovered on its way out of the solar system after its closest approach to the Sun, Borisov's comet was discovered while it was still approaching the Sun. This gave scientists a precious gift: time. They had months to plan observations, to coordinate telescope time, to prepare instruments and experiments. The comet would reach perihelion, its closest point to the Sun, on December 8, 2019, more than 3 months after discovery. That meant there would be an extended window for studying this visitor from another star system. As observations accumulated through September and October, 2I Borisov revealed itself to be very different from Oumuamua. For one thing, it looked like a normal comet. It had a bright, fuzzy coma surrounding its nucleus, and it developed a long tail as it approached the Sun. Spectroscopic observations showed that the coma contained water vapor, cyanogen and diatomic carbon, all common ingredients in comets from our own solar system. Later observations detected carbon monoxide as well. The comet was behaving exactly as comets are supposed to behave. When the Sun heats them up, they release gas and dust, creating the characteristic features that make comets so beautiful to observe. Scientists were both relieved and slightly disappointed. Relieved because 2I Borisov was acting predictably, confirming that at least some interstellar objects are just normal comets that happen to have been ejected from their home systems. Disappointed because there's always a hope, especially after the strangeness of Oumuamua, that each new discovery might reveal something completely unexpected about the universe. Still, even though 2I Borisov looked like a normal comet, studying it was incredibly valuable because it allowed direct comparisons between objects from our solar system and objects from other star systems. One of the first things scientists wanted to know was what 2I Borisov was made of. They used powerful spectrographs attached to large telescopes to analyze the light coming from the comet's coma. Different molecules absorb and emit light at specific wavelengths, creating patterns that serve as chemical fingerprints. By carefully measuring these patterns, astronomers can figure out exactly what gases a comet is releasing. For 2I Borisov, the results were fascinating. The comet appeared to be rich in carbon monoxide, much more so than typical comets from our solar system. In fact, the ratio of carbon monoxide to water was among the highest ever measured in any comet. This suggested that 2I Borisov formed in a very cold region of its home star system, far from its parent star where carbon monoxide ice is stable. Researchers also studied the dust coming off 2I Borisov. Using polarimetry, a technique that measures how light waves vibrate as they reflect off particles, scientists determined that the dust grains were larger and more compact than typical cometary dust in our solar system. The dust particles were probably at least a few micrometers across, perhaps 10 times larger than average solar system comet dust. This difference might reflect something about how dust forms and evolves in different planetary systems, or it might just be natural variation among comets. The colour of 2I Borisov was another interesting feature. The nucleus appeared reddish, similar to many objects in the outer solar system that have been exposed to cosmic radiation for billions of years. The coma and tail also had a slight reddish tint. This colour comes from complex organic molecules, carbon-based compounds created when ultraviolet light and cosmic rays interact with simple ices like water and methane. The fact that 2I Borisov had this reddish colour suggested it had been travelling through interstellar space for a very long time, long enough for its surface to be thoroughly processed by radiation. Scientists attempted to measure the size of 2I Borisov's nucleus, but this proved challenging. The nucleus was surrounded by a bright coma, making it difficult to see the solid object at the centre. Based on the amount of sunlight reflecting off the comet and assumptions about how reflective its surface might be, researchers estimated the nucleus was probably between 200 meters and 1 kilometer across. That's roughly the size of a small mountain, much bigger than most Earth mountains are wide at their base, but tiny compared to planets or even large asteroids. As 2I Borisov approached its closest point to the Sun in early December 2019, its activity increased dramatically. The rate of gas and dust release went up, and the coma grew larger and brighter. Telescopes around the world trained on the comet, capturing beautiful images that showed the graceful curve of its tail sweeping away from the Sun. The Hubble Space Telescope took multiple pictures, showing incredible detail in the coma's structure. These images revealed that the coma wasn't perfectly smooth. There were subtle variations in brightness and structure. possibly indicating that different parts of the nucleus were releasing gas at different rates. This is common in comets because their surfaces are usually patchy, with some areas covered in ice and others covered in dust or rock. Then, in mid-March 2020, something unexpected happened. Astronomers noticed that 2I Borisov was undergoing what's called an outburst. Suddenly, the comet brightened significantly, releasing a large pulse of gas and dust. Follow-up observations with Hubble revealed that the nucleus had actually split into at least two pieces. One piece was much brighter than the other, suggesting it was larger or more active. The smaller fragment was much fainter and gradually faded from view over the following weeks. Cometary fragmentation isn't unusual. The stresses of being heated by the sun, combined with the escape of gas from below the surface, can crack a comet's nucleus and break it apart. Several comets in our solar system have been observed to split, sometimes into dozens of pieces. But witnessing this happen to an interstellar comet was special because it provided insights into the internal structure and strength of these objects. The fragmentation event told scientists that 2I Borisov's nucleus was probably quite weak structurally, held together by gravity, and maybe some internal ices but not by strong rocky materials. This matches what we know about many solar system comets, which are often described as dirty snowballs, mixtures of ice, dust and small rocks that are only loosely bound together. The fact that 2I Borisov broke apart reinforced the idea that interstellar comets, or at least this one, are fundamentally similar to local comets, just born in a different star system. One of the most exciting aspects of 2I Borisov was the opportunity to trace its origins. Unlike Oumuamua, which gave astronomers only a brief glimpse before disappearing, 2I Borisov was observed extensively over many months. This allowed for very precise measurements of its orbit. Scientists calculated the trajectory backward through the galaxy, accounting for the gravitational influences of the Sun, the planets, nearby stars, and the overall structure of the Milky Way. The calculation suggested that 2I Borisov came from the direction of a star called Kruger 60, a binary star system about 13 light-years from Earth. However, the uncertainty in the trajectory was large enough that other nearby stars couldn't be ruled out. One thing was clear, though. 2I Borisov had been travelling through interstellar space for millions of years before entering our solar system. Think about what that means for a moment. 2I Borisov was ejected from its home system millions of years ago, possibly even longer. At that time on Earth, humans were just beginning to evolve. Our ancestors were still primitive primates living in trees. No cities existed, no written language, no telescopes. While human civilization slowly developed over millions of years, 2I Borisov was silently drifting through the empty space between stars, frozen and dormant, waiting. It passed through clouds of gas and dust, through regions where stars were being born, through the spiral arms of our galaxy, and then, in 2019, it happened to pass close enough to the Sun to wake up and start outgassing, and we happened to be watching with telescopes advanced enough to spot it. The timing is staggering when you think about it. By mid-2020, 2I Borisov had passed its closest approach to the Sun and was heading back out toward interstellar space. Telescopes continued tracking it as long as possible, but eventually it became too faint to see. The last observations were made in mid-2020, nearly a year after discovery. By then, the comet had reached the orbit of Jupiter and was fading into the darkness. It's now gone, invisible even to our most powerful instruments, travelling outward into the Oort cloud and beyond. Someday, centuries from now, it will cross the boundary of the solar system and return fully to interstellar space, carrying with it a tiny bit of heat and perhaps a few molecules of gas from our Sun. The legacy of 2I Borisov is different from Oumuamua's, but equally important. Where Oumuamua raised questions and sparked controversies, 2I Borisov provided answers and confirmed expectations. It showed that at least some interstellar objects are completely normal comets that behave in understandable ways. It demonstrated that comets from other star systems can be similar in composition and structure to our own solar system's comets, suggesting that the basic processes of planet and comet formation might be universal. It also showed that with proper preparation and enough warning time, we can study these visitors in great detail, extracting valuable scientific data that helps us understand not just individual objects, but the broader population of interstellar wanderers drifting through the galaxy. 2I Borisov also holds a special place in history as the first interstellar object discovered by an amateur astronomer. Gennady Borisov's patient work, scanning the skies night after night with his homemade telescope, reminds us that important discoveries don't always come from billion-dollar observatories or professional research teams. Sometimes they come from dedicated individuals who love the night sky and are willing to spend cold nights under the stars looking for something new. Borisov's name will forever be associated with the second interstellar visitor, a fitting tribute to his passion and skill. Let's shift our attention from interstellar objects to something that actually hit Earth, though we still don't fully understand what it was. On June 30th, 1908, at about 7 in the morning local time, something exploded in the sky over a remote region of Siberia called Tunguska. The explosion was enormous, equivalent to somewhere between 3 and 15 megatons of TNT, which is roughly 1,000 times more powerful than the atomic bomb that destroyed Hiroshima. The blast flattened about 80 million trees across more than 2,000 square kilometers of forest. Witnesses up to 60 kilometers away reported being knocked off their feet. People hundreds of kilometers away saw a fireball in the sky brighter than the sun. The shockwave traveled around the world multiple times, recorded by barometers in Europe and Asia. Despite the immense power of the explosion, it happened in such a remote area that relatively few people witnessed it directly. The nearest town, Vanavara, was about 60 kilometers away. The region was sparsely populated, inhabited mostly by indigenous Evenki people who lived as reindeer herders. In the immediate aftermath, there was confusion and fear, but limited investigation. Russia was going through political turmoil at the time, and World War I and the Russian Revolution would soon consume the nation's attention. It wasn't until 1927, nearly 20 years after the event, that the first scientific expedition reached the site. When scientists finally arrived at Ground Zero, they found a scene of apocalyptic devastation. Trees were knocked down in a radial pattern, all pointing away from the centre of the blast. At the very centre, within about 8 kilometres of the explosion point, trees were still standing but had been stripped of their branches and bark, reduced to bare poles. The blast had literally seared the vegetation off them while the downward force of the shockwave prevented them from falling over. Beyond that central zone, the fallen trees stretched to the horizon in every direction, like matchsticks knocked over by a giant hand. The first surprise was what researchers didn't find. There was no crater. Meteorite impacts always leave craters, depressions in the ground created when the space rock smashes into the surface. The absence of a crater was puzzling, and immediately suggested that whatever caused the Tunguska explosion had detonated in the air, above the ground. Later analysis of the treefall patterns confirmed this. By carefully mapping which direction trees had fallen, scientists estimated that the explosion occurred at an altitude of about 5 to 10 kilometers above the surface. The second surprise was the lack of meteorite fragments. When large space rocks enter Earth's atmosphere, they usually break apart due to the intense heat and pressure, and pieces rain down over a wide area. Meteorite hunters should have found chunks of iron or stone scattered around the Tunguska site, but despite extensive searches over many decades, no definitive meteorite fragments have ever been recovered. Some researchers have found tiny particles of unusual minerals in the soil that might be meteoritic, but nothing conclusive. The absence of large fragments reinforced the idea that the object exploded at high altitude, and whatever was left was pulverized into microscopic dust. So what was it? Over the past century, dozens of theories have been proposed, ranging from the scientifically plausible to the completely absurd. The most widely accepted explanation among scientists is that a small asteroid or comet nucleus entered Earth's atmosphere at high speed, probably travelling at least 50,000 kilometers per hour. The object was likely about 30 to 60 meters across. As it plunged through the atmosphere, the air in front of it couldn't get out of the way fast enough and compressed into a superheated plasma. The intense heat caused the object's surface to melt and vaporize. The internal stresses from rapid heating and the crushing pressure of the atmosphere caused the object to break apart and explode at an altitude of 5 to 10 kilometers. The explosion released its kinetic energy all at once, creating a massive shockwave that devastated the forest below. This explanation fits most of the evidence. An airburst explosion would explain the lack of a crater and the radial treefall pattern. The vaporization of the object would explain the absence of meteorite fragments. The altitude of the burst, high enough that the shockwave weakened by the time it reached the ground, would explain why there was no significant excavation of soil. Computer simulations of such an event match the observed damage patterns reasonably well. But there are complications. For one thing, if the object was a stony asteroid, typical of the majority of asteroids that cross Earth's orbit, it should have been strong enough to survive deeper into the atmosphere before breaking apart. To explode at 5 to 10 kilometers altitude, the object would need to be unusually weak. This has led some researchers to propose that the Tunguska impactor was a comet nucleus, rather than an asteroid. Comets are much weaker structurally because they're made mostly of ice, with embedded dust and rock, held together loosely by gravity. A comet nucleus entering the atmosphere at high speed would break apart and explode at a higher altitude than a rocky asteroid. The problem with the comet theory is that comets approaching the Sun usually develop visible tails that would have been seen from Earth in the days or weeks before the impact. No such comet was reported, though it's possible nobody was looking in the right part of the sky. Some scientists have proposed that the object was actually quite small, maybe only 10 to 15 meters across, but made of very weak material like a carbonaceous asteroid or an extinct comet nucleus. Objects this small can be difficult to detect even with modern telescopes, so it's plausible nobody saw it coming. The weak structure would allow it to break apart high in the atmosphere, consistent with the evidence. Other researchers think the object might have been larger, 50 to 100 meters across, but entered the atmosphere at a shallow angle, skipping along like a stone on water before finally exploding. This trajectory would explain some eyewitness accounts of a prolonged fireball that moved across a large arc of sky. Then there are the more exotic theories. One idea that gained some traction in the past was that a small black hole passed through Earth, entering the atmosphere over Tunguska and exiting somewhere in the Atlantic Ocean. The gravitational stresses from a microscopic black hole might produce effects similar to an explosion. However, this theory has been thoroughly debunked because a black hole would have created seismic waves when it passed through the Earth that weren't observed, and the exit point should have produced another atmospheric explosion that didn't happen. Another wild theory suggested that the explosion was caused by a chunk of antimatter from space. When matter and antimatter meet, they annihilate each other in a burst of pure energy. But antimatter doesn't exist naturally in large quantities in our region of space, and there's no evidence of the unique radiation signature that matter-antimatter annihilation would produce. The most extreme theory, proposed by some fringe researchers, claims that the Tunguska event was caused by the explosion of an alien spacecraft. Supposedly, a damaged extraterrestrial vessel was attempting to make an emergency landing on Earth and exploded over the unpopulated Siberian wilderness. Proponents point to the lack of meteorite fragments as evidence that the object wasn't natural. However, this theory requires us to assume that aliens exist, that they were visiting Earth in 1908, that their technology was advanced enough for interstellar travel, but still capable of failing catastrophically, and that they left absolutely no other evidence of their presence. As with 3I Atlas and Oumuamua, the principle of Occam's razor suggests we should prefer simpler explanations that don't require such extraordinary assumptions. The Tunguska event reminds us that Earth is constantly being bombarded by space debris. Most of it is tiny, dust-sized particles that burn up harmlessly in the upper atmosphere as meteors. Larger chunks, pebble-tube basketball-sized, hit the atmosphere regularly but usually disintegrate before reaching the ground. Objects the size of cars strike Earth's atmosphere several times per year, producing bright fireballs that are sometimes caught on camera. But objects large enough to cause significant ground damage like the Tunguska impactor are much rarer. Scientists estimate that Tunguska-scale impacts happen somewhere on Earth about once every few hundred years on average. The last one happened to hit a remote forest where almost nobody lived. The next one might not be so fortunate. This brings us to an important point about planetary defense, the effort to detect and potentially deflect asteroids that might threaten Earth. The Tunguska event showed that even relatively small objects can cause immense destruction if they hit a populated area. A Tunguska-sized explosion over a major city would kill millions of people instantly and create economic and social chaos. The good news is that NASA and other space agencies now operate surveys that scan the sky looking for asteroids that might cross Earth's orbit. These surveys have found and tracked thousands of near-Earth asteroids, and they're constantly discovering more. The current goal is to find at least 90% of near-Earth asteroids larger than 140 meters across, big enough to cause regional devastation if they hit. So far, the surveys have found most of the really large ones, the kilometre-sized objects that could cause global catastrophes, and none of them pose a threat for at least the next century. But smaller objects like the Tunguska Impactor are harder to find because they're dimmer and more numerous. There are probably tens of thousands of Tunguska-sized asteroids out there, and we've only found a small fraction of them. Interestingly, the Tunguska event also connects to our discussion of interstellar objects in a subtle way. Some researchers have proposed that a small percentage of near-Earth asteroids might actually be captured interstellar objects, visitors from other star systems that happened to get caught by the Sun's gravity and ended up in orbits around the Sun. If this is true, then some of the asteroids we track as potential Earth impactors could be messengers from distant stars, though most are certainly natives of our solar system. There's even been speculation, though it's highly uncertain, that the Tunguska Impactor itself might have been an interstellar object. The unusual lack of fragments and the apparent weakness of the object could potentially fit with an interstellar comet nucleus. However, there's no way to prove this more than a century after the event, and most scientists think it was probably just a normal comet or asteroid from our own solar system. The Tunguska event serves as a reminder that the dangers from space are real, not just science fiction. Earth has been hit by large objects many times in the past. The most famous example is the Chicxulub Impactor, a 10-kilometre-wide asteroid that struck Mexico 66 million years ago and caused the extinction of the dinosaurs. But there have been many other impacts throughout Earth's history, most of them smaller than Chicxulub but still capable of causing significant regional destruction. As we learn more about the population of near-Earth asteroids and develop better detection systems, we're taking the first steps toward protecting our planet from future impacts. The knowledge we gain from studying objects like 3I Atlas, Oumuamua, and 2I Borisov contributes to this effort by helping us understand what these wandering space rocks are made of and how they behave. Now let's talk about a place that's technically part of our solar system but is so distant that we've never actually seen it directly. This mysterious region is called the Oort cloud, and it's thought to be the source of most long-period comets, those comets that take hundreds or thousands of years to orbit the Sun. Understanding the Oort cloud helps us understand where interstellar visitors like 3I Atlas might have come from, because their home systems probably had similar structures. Picture the solar system as a series of shells or layers. At the centre is the Sun. Close to the Sun are the inner planets, Mercury, Venus, Earth and Mars, all orbiting within about 230 million kilometres of the Sun. Farther out are the giant planets, Jupiter, Saturn, Uranus and Neptune, orbiting between about 800 million and 4.5 billion kilometres from the Sun. Beyond Neptune lies the Kuiper Belt, a disk of icy objects that includes Pluto and thousands of other small worlds. The Kuiper Belt extends from about 4.5 billion kilometres to roughly 7.5 billion kilometres from the Sun. But that's not the end of the solar system. Far, far beyond the Kuiper Belt, beginning at roughly 2,000 times Earth's distance from the Sun, and extending perhaps halfway to the nearest star, lies the Oort cloud. This enormous spherical shell of icy debris completely surrounds the solar system in all directions. If you could see it from outside, the solar system would look like a tiny bright dot, the Sun, surrounded by a huge fuzzy sphere of faint comets, like a tennis ball sitting inside a basketball arena. The Oort cloud has never been directly observed because the individual objects that make it up are too small and too far away to see with current telescopes. We infer its existence from studying the orbits of long-period comets. When astronomers trace these comets' paths backward, they find that the comets are coming from all directions in space, not just from the flat plane where the planets orbit. This suggests there's a spherical shell of comets surrounding the Sun. Moreover, the comets seem to come from distances of tens of thousands of times Earth's distance from the Sun. Put these two observations together, and you get the Oort cloud. Scientists estimate there are trillions of icy objects in the Oort cloud, maybe even more. Most of them are small, probably ranging from 1 kilometre to a few tens of kilometres across. The total mass of the Oort cloud is uncertain, but estimates suggest it might contain somewhere between a few Earth masses and several dozen Earth masses worth of material, though that material is spread out over an absolutely enormous volume of space. The density is incredibly low. If you were standing on an Oort cloud object, the nearest neighbouring object might be tens of millions of kilometres away, and you'd have no way to see it without a powerful telescope. How did the Oort cloud form? The story begins 4.5 billion years ago, when the solar system was young. Back then, the region around the Sun was filled with a disk of gas and dust left over from the cloud that formed the Sun. Within this disk, solid particles began sticking together, gradually building up larger and larger objects. Close to the Sun, where it was hot, only rocky materials and metals could remain solid, so the inner planets formed from rock and metal. Farther out, where it was colder, water and other volatile compounds could freeze, so the outer planets and their moons formed from mixtures of rock and ice. As the giant planets Jupiter, Saturn, Uranus and Neptune grew, their powerful gravity stirred up the remaining debris in the outer solar system. Many small icy bodies were flung away by close gravitational encounters with these planets. Some were thrown inward toward the Sun where they might have hit planets or been destroyed. Others were thrown outward at high speed. Those that were thrown outward but not quite fast enough to escape the Sun's gravity entirely ended up in very elongated orbits, swinging far out into space before falling back toward the Sun millions of years later. Over time, these objects accumulated in a spherical shell around the solar system, the Oort cloud. The distant tugs of passing stars and the overall gravitational field of the Milky Way galaxy then gradually rounded out their orbits, creating the spherical distribution we see today. The Oort cloud is divided into two parts. The inner Oort cloud, sometimes called the Hills cloud, after the astronomer who first proposed its existence, extends from about 2,000 to 20,000 times Earth's distance from the Sun. This region is shaped more like a thick disk than a sphere, with more objects concentrated near the plane of the solar system. The outer Oort cloud extends from 20,000 times Earth's distance from the Sun to perhaps 100,000 times or more, reaching about 1.5 to 2 light-years from the Sun. This outer region is more spherical, with objects distributed fairly evenly in all directions. Occasionally, something disturbs an Oort cloud object, changing its orbit so that it falls inward toward the Sun. The disturbance might come from the gravity of a passing star, since stars occasionally pass within a light-year or two of the Sun as they orbit through the galaxy, or it might come from the collective gravitational field of the Milky Way itself, which can nudge distant objects over millions of years. When an Oort cloud object falls toward the inner solar system for the first time, astronomers call it a dynamically new comet. These comets often behave unpredictably, because they're being heated by the Sun for the first time in billions of years, and nobody knows exactly how their surfaces will respond. Some of these long-period comets swing around the Sun once and then return to the Oort cloud, not to be seen again for thousands or millions of years. Others have their orbits altered by close encounters with Jupiter or the other giant planets. A lucky few get caught in shorter orbits that keep them in the inner solar system. These become short-period comets, returning every few decades or centuries. Halley's Comet, probably the most famous comet of all, is an example. It returns to the inner solar system every 76 years and has been recorded by humans for more than 2,000 years. Halley's Comet probably originated in the Oort cloud, but had its orbit shortened by gravitational interactions with planets. Now here's where the connection to interstellar objects becomes clear. Other star systems almost certainly have their own Oort clouds, shells of icy debris left over from planet formation. When giant planets form and migrate in those systems, they fling debris outward just like Jupiter and Saturn did here. Some of that debris gets captured into distant orbits, forming Oort clouds around other stars, but some of it gets thrown so hard that it escapes the star system entirely and becomes an interstellar wanderer. These are the objects like Oumuamua, 2I Borisov, and 3I Atlas, comets and asteroids that were kicked out of their home systems and have been drifting through the galaxy ever since. By studying comets from our own Oort cloud and comparing them to interstellar visitors, scientists can learn about how typical or unusual our solar system is. Do comets from other stars have similar compositions to our comets, or are there fundamental differences? Are the processes that formed our Oort cloud universal, or does each star system evolve differently? These questions drive much of the research on interstellar objects. Every new discovery adds one more data point, helping to build a statistical picture of what planetary systems across the galaxy look like. There's also a fascinating speculation that some scientists have explored. Could life ever exist in the Oort cloud or in the spaces between stars? At first, this seems absurd. The Oort cloud is incredibly cold, far from the Sun's warmth, and starlight is too dim to provide energy. But some researchers have proposed that liquid water might exist beneath the surfaces of the largest Oort cloud objects. Heat from radioactive decay in the rocky cores of these objects could potentially melt ice, creating subsurface oceans similar to those believed to exist on Jupiter's moon Europa and Saturn's moon Enceladus. If such oceans exist and if they contain the right chemical ingredients, could microbial life potentially survive there? It's pure speculation, but not completely impossible according to our understanding of biology and chemistry. Taking the idea further, if life could survive in the subsurface oceans of Oort cloud objects, then when those objects get ejected from their star systems and become interstellar wanderers, they might carry life with them. An interstellar comet could theoretically transport microbes from one star system to another, a process called panspermia. If such a comet fell into another star system and collided with a habitable planet, it might seed that planet with life. Some scientists think this could be a mechanism for spreading life throughout the galaxy, though there's no evidence that it actually happens. The challenges are enormous. Microbes would need to survive millions or billions of years frozen in ice. They'd need to survive bombardment by cosmic radiation. They'd need to survive the violent entry into a new star system and impact with a planet. But life on Earth has proven to be remarkably resilient. Some Earth microbes can survive extreme cold, extreme radiation, and long periods of dormancy. So maybe, just maybe, interstellar panspermia is possible. If that's true, then objects like 3I Atlas aren't just interesting astronomical curiosities. They could be the mechanism that makes life a galactic phenomenon rather than isolated to individual worlds. Let's turn our attention to an object that definitely belongs to our solar system, but has caused plenty of excitement and worry over the past 2 decades. This is the asteroid Apophis, officially designated 99,942 Apophis. Discovered in June 2004 by astronomers at the Kitt Peak National Observatory in Arizona, Apophis is a near-Earth asteroid about 340 meters across, roughly the size of 3 football fields placed end to end. That might not sound very large compared to mountains or even large buildings, but in space, an object that size moving at tens of thousands of kilometers per hour carries enormous energy. When Apophis was first discovered, astronomers calculated its orbit and realized something alarming. The asteroid's path would bring it very close to Earth on April 13th, 2029. Initial calculations showed a small but real chance that Apophis might actually hit Earth. As more observations came in over the following months, the predicted path was refined and the probability of impact went up. At one point, Apophis briefly held the highest rating on what's called the Torino scale, a system that ranks the threat level of near-Earth objects from 0, no threat, to 10, certain collision with global consequences. Apophis reached level 4, which indicates a close encounter that merits attention from astronomers, but isn't yet certain to cause damage. The news media picked up the story, and for a while, Apophis became famous as